An acid-base titration is a method for finding the concentration of an acid or a base when you don't know it, but you do know the concentration of another solution that reacts with it. The entire idea rests on counting moles through a neutralization reaction. At the chemical level, acids and bases react in fixed ratios. In the simplest case, hydrogen ions react with hydroxide ions to form water. H+ reacts with OH- to make H2O. For a common lab example, hydrochloric acid reacts with sodium hydroxide in a 1:1 ratio. 1 mole of acid reacts with 1 mole of base. That fixed ratio is what makes titration reliable. In the lab, the solution with unknown concentration is called the analyte. A precise volume of it is measured with a pipette and placed into a conical flask. The solution with known concentration is called the titrant, and it goes into a burette so it can be added very precisely, drop by drop. As the titration begins, titrant is added while the flask is swirled to keep everything mixed. Each drop reacts immediately. Early on, nothing dramatic happens because there is still plenty of analyte left. As more titrant is added, the analyte is steadily used up according to the balanced equation. Eventually, you reach the equivalence point. This is the theoretical point where the amount of titrant added contains exactly the number of moles needed to react with all of the analyte, based purely on stoichiometry. You can't see the equivalence point directly, so instead you observe the endpoint. The endpoint is detected using an indicator or a pH meter. An indicator is a weak acid or base that changes color over a narrow pH range. The key is choosing an indicator whose color change happens very close to the equivalence point. When the color change persists, you stop the titration. A good indicator makes the endpoint and equivalence point almost the same. Once you stop, you record the volume of titrant used. The calculation follows a fixed logic. First, convert the titrant volume into moles using its known concentration. Second, use the mole ratio from the balanced equation to find how many moles of analyte were present. Third, divide by the analyte's volume to get its concentration. The shape of the pH change depends on the acid and base involved. Strong acid, strong base titrations have a sharp pH jump, making indicator choice flexible. Weak acid, strong base titrations have a buffer region and a basic equivalence point, so indicator choice matters more. In one sentence, an acid-base titration works by carefully adding a known solution to an unknown one until stoichiometric neutralization is reached, detecting that moment with a sharp pH change, and using mole ratios to calculate the unknown concentration.